Hi everyone, welcome to part 3 of our series on optimization, where we look at how to maximize or minimize certain quantities in a contextualized scenario. If you haven't watched part 2 or part 1 of this series, the idea of what we're doing is we're taking some random function, this is f of x, and we are finding the points where there's a potential maximum or minimum, where the function appears to max out or minimize. In other words, where does it switch from increasing to decreasing or decreasing to increasing? Those points are when we see a slope of a tangent line of 0, or, in other words, the derivative at that point is 0. Optimization applies this to contextual scenarios. This is obviously a bit more hypothetical, but the idea still remains the same. So let's take a look at this problem that we have. It says that an isosceles triangle is inscribed inside the parabola y equals 27 minus x squared, just like this, as per the figure shown on the left. What is the maximum possible area and the resulting perimeter of the triangle? So notice the wording in the question here. We're not finding the maximum perimeter, we're finding the perimeter of the triangle with maximized area. It's a bit wordy, but who cares? So let's go ahead and just split this into two parts here. So this is the area. So the area part, what we need to do is we need to take a look at this triangle right here. So we see that the triangle intersects the curve at this point right here, at this corner. And we notice that this part right here is the x value of the triangle. And this part is the x value of the point. Sorry, not the triangle. This point right here, the vertical part of this point, is the y value of that point. So in other words, we can find what our base and our height is, and that's what we can use to find the area of the triangle. So the base of this whole triangle is this part of x plus this part of x. Now we know that this is isosceles, so this means that this length right here, x, is half of the base. So this length right here is also x. In other words, the base of the triangle is 2 times x. And the height of the triangle, we see that the height at this point is the same length as the height at this point right here. So the height is just y. So the area of this triangle, so the area of the triangle is 1/2 base times height, right? So this is going to be 1/2 times 2x times y. And so we get the area is equal to just xy. It's pretty convenient, right? Now here's what we need to do. We need to find some way to substitute x or y into somewhere so that we can get a properly differentiable function. Thankfully, we have this constraint right here. Y is equal to 27 minus x squared. So we can substitute this expression in here for y, because again, we have a point on the curve and it works. So this means that the area is equal to x times 27 minus x squared. So the area function works out to be 27x minus x cubed. Now all we have to do is the actual calculus part and solve for the zeros. That is taking the derivative. So the area prime is going to be equal to 27 minus 3x squared, and this works out to be 0. So now all we have to do is just solve for x. So we get that 3x squared is equal to 27, and x squared is equal to 9. You divide out 3 on both sides, and then we get that x is equal to plus or minus 3. Now we can go ahead and just disregard this negative root because the base length should be a positive value. So we're going to have x equals positive 3. And so here's what all we have to do now. We just have to substitute this value of x in for our area equation right here. So we get that area, which we'll call area max. This is equal to 27 times 3 minus 3 cubed. And this works out to be 81 minus 27. And so area maximum is going to be 54. And that is the maximum area of this triangle. So now that's part 1 complete. Let's go ahead and move on to part 2. Part 2 is the perimeter So the perimeter is a bit interesting for this triangle. We know that it's isosceles, meaning that these two, here, I'll show it a little bit clearer. These two side lengths are equal, and we know what the base length is already. It's just 2 times the x value. So the perimeter we can write as 2x plus, or here, not 2x yet. We'll just leave this in general terms yet, right now. This is the base plus 2, and I'll call this s. So what do we know? We know that b is 2x, but what is s? Well, s is going to be the length of this side right here. Now we know that it has a horizontal leg of x and a vertical leg of y. So we can just use Pythagorean to find what s is. So s is going to be equal to the square root of x squared plus y squared. And we can we can say that y is 27 minus x squared. So we can say that this is x squared plus 27 minus x squared squared. And we can just leave it like this because we're going to be plugging in values later. I'm just doing this way right now, so we only have to plug in one thing. So things are a lot easier. So now we know that the perimeter is going to be, here, I need to capitalize that. So now we know that the perimeter is going to be the base plus 2 times the side length. So it's going to be 2x plus 2 root x squared plus 27 minus x squared, all that squared. So the resulting perimeter is going to be, I'll call this P3. So this is going to be 2 times 3 plus 2 times the square root of 3 squared plus 27 minus 3 squared, all that squared. So this is going to be 6 plus 2 root 9 plus 324, which is 18 squared. And then we get that P is going to be equal to 6 plus 2 root 333. So this one wasn't really calculus based at all. If your teacher was really devilish, you might see the perimeter being maximized. You notice that this is our equation for the perimeter. If you had to differentiate this would be a very complicated algebraic equation to solve. Maybe you might see it for a calculator question, maybe not for a non-calculator question. But yeah, so this right here is just another scenario in which optimization can be used. And we will be looking in a couple more parts on how optimization can be used in other scenarios. So that's it for this video. I hope to see you in future videos.